Cosmic Dawn into the title. I didn't have it in my original title. So, mission accomplished. Thank you, everybody, and thank you to the organizers for inviting me here. I'm really happy to be giving this talk after the talks that we've had both this morning and this afternoon, because they've, between Peter and Crystal and Jake and Anna Christina this morning and other talks, it's just really set things up for being excited about what we can learn about galaxies from studying their clustering and from studying their environments. So I hope I don't have to convince you that that's interesting. And I'll say a little bit about what has been done so far with JWST in this area and what some of the potential is for the future. This is not JWST, and this is not Cosmic Dawn. This is the sort of state of the art right now for, well, let's call it the low redshift universe. But anyway, out to redshifts of 2, the DESI instrument, the dark energy spectroscopic instrument on the Mayall 4 meter at KITP, is in a 5-year survey that will ultimately measure 37 million galaxy redshifts and 2.5 million quasar redshifts out to redshifts of 2 or so. And of course, a lot of this is being driven by cosmology goals. But in terms of characterizing a lot of things about large-scale structure in amazing statistical detail, these wide-field experiments like DESI, PFS, Weave, Foremost, etc., are tremendously, tremendously powerful tools. I may touch, if I have time, briefly on other wide-field things for the future later. But this will set an amazing baseline of understanding about large-scale structure at low redshift for comparing what we learn at high redshift. And where does JWST fit into this? Well, it is, as you've heard, a very powerful tool for studying cosmic dawn, thanks really to the combination of imaging and spectroscopy. So JWST enables both the discovery of galaxies at cosmic dawn out to the highest redshifts we know today, and also their spectroscopic confirmation. It's not just little faint blobs with photometric redshifts anymore. We have spectra of these things, and we actually know whether or not they are at the redshifts we said they were at. From imaging alone, we get photometric redshifts. It's a very powerful tool for that, and that can be used to study clustering through angular correlations based on photometric redshifts and environmental densities. We'll talk somewhat about that, but it's really spectroscopy that's the transformational tool here, giving us accurate redshifts and also detailed spectral properties of the galaxies that we can then maybe or maybe not relate to things about their environments. The main instruments that you've heard about during the course of this meeting for this kind of spectroscopy are especially NIRSpec, which has the multi-object spectroscopic capability from 1 to 5 microns that's enabled a lot of the amazing spectra you've seen here. But also, we heard today quite a bit about the NIRCam slitless spectroscopy, the GRISM spectroscopy, that gives us large unbiased samples of emission line objects, and is really, as you heard from Jake and Anna Christina, a very powerful tool for studying structure and environment. So all of these instruments together make it surprisingly easy to get spectroscopic redshifts for galaxies, especially strong emission line galaxies, out to redshifts of 9.5. Beyond that, the strong optical rest frame lines like H alpha and oxygen 3 redshift beyond the range of these instruments, and it starts getting more challenging and also more interesting in some ways, so we'll touch on that again later. Spectroscopy for studying cluster and environment gives us robust, if not necessarily complete, redshift measurements with quantifiable accuracy, which then translates to robust measurements of the line of sight distance and the accuracy of that. Reduces and eliminates foreground, background contamination for membership in structures over densities, clusters, groups, etc., and for projected correlation measurements. Direct measurement of 3D spatial clustering, identification of individual over densities, groups, clusters, voids, filaments, over and under densities. And then, as I mentioned before, it lets us characterize properties of galaxies and then study those properties with respect to local environment. And here's a laundry list of many different properties that we might be interested in studying in relation to the galaxy environment. We'll touch on a few of these as we go along. So let's look back before JWST and a little bit about clustering measurements at high redshift. So Lyman break galaxies are near and dear to my heart and that of many others. And from the early, and it was really, Lyman break galaxies were one of the first populations of high redshift galaxies where we could actually find enough of them to make a statistical sample that you could use to measure clustering with. I mean, you just couldn't do that when you had one or two quasar companions or something like that, or a radio galaxy or two. As much as I love the radio galaxies, you know, you couldn't do this kind of work. But once you had hundreds and then thousands of Lyman break galaxies, you could actually start studying their clustering properties. And here's a whole lot of papers that have done that over the years, dating back to the early days of Lyman break galaxies. And the kinds of things that were measured early on. So here are early measurements of the correlation function, the correlation length of Lyman break galaxies at redshifts of 3 as a function. As you go fainter, they become less correlated. The correlation length gets smaller. I like this plot because it shows that back in 2001, we were still plotting things for 3 different cosmologies, just because, you know, we wanted to hedge our bets. So that's changed now. And once we had even larger samples, denser samples of Lyman break galaxies down to fainter magnitudes from especially HST surveys, we could start breaking that correlation function down into these 2 halo and 1 halo term that Peter was referring to. You could see this differences in the small scale and large scale correlations that are due to the population of satellite objects as opposed to the correlations of independent dark matter halos. From Lee et al. And then from deriving these clustering strengths and comparing it to dark matter clustering strengths, Peter described this, you can estimate the bias of the galaxy population. This is a very typical thing that people try to do with these studies. And in this case, people were measuring bias levels of about 3 for the galaxies that make up these Lyman break galaxy populations. And this work has continued with deeper and higher redshift HST surveys going out to redshifts of 7 or so with WFC3 based studies. And then here's a few more recent studies using HST data pushing out to redshifts of almost 8 or so. But that was about the limit of where you could get enough objects robustly detected with photometric redshifts to do this kind of work with HST. Lyman alpha emitters are another popular tool for studying galaxy clustering at high redshift. It's another thing that, especially if you have wide field imagers, you can get lots and lots of these, and Subaru has really been the premier tool for this, but now dark energy camera is also a very powerful tool for getting large narrowband studies. And it turns out that even early on, people determined that the clustering of Lyman alpha emitters was weaker, corresponding to them being in lower mass and lower bias galaxy systems. People were measuring bias values of about 2 or less, back to Gaweiser et al. 2007. And the narrowband imaging gives you narrow slices in redshift compared to, say, Lyman break galaxies or photometric redshifts. And so it's actually nice to be able to take a slice through the universe and then map out this kind of filamentary and protocluster structure that is seen in these kinds of data sets. This is a famous protocluster at a redshift of 3.1 that's been studied to death with just a few references here. Yamada et al. Did this beautiful early Subaru map showing these overdensities, underdensities, and filamentary structures. This is more recent data from a survey called Odin. That's a dark energy camera survey that's going to cover 100 square degrees in narrowband data at redshift of 3. Kyung-Soo Lee is the PI of this. And recently, DESI has been turned on to take spectra of those Lyman alpha emitters, and they're measuring correlation functions with spectroscopic data in this case, 4,000 Lyman alpha emitters over 9 square degrees from the Odin survey, and coming up with low bias values very similar to what people had previously derived. So what about JWST? This is not cosmic dawn either, but it's a beautiful picture, and I just wanted to show it because this was one of the, I thought, prettiest pictures that came out of the Sears imaging program. I'm mostly going to talk about spectroscopy, but this is from Rose Coogan et al., who studied a group of galaxies at redshift 1.85 in the extended growth strip. Spectacular. Many of these have spectroscopic conformation, these galaxies here. And if you stretch and filter this image, you find good detection of intercluster light within this group at redshift 1.85. And there's interesting things to learn about the dynamical history of the cluster and the stellar populations that make up this intercluster light. And there's all sorts of other cool stuff going on here with dusty star formation and dusty starbursts and AGN and lots of stuff. So this is an interesting paper if you want to see a laboratory for what you can do, very high quality detailed work. But I'm going to get back to cosmic dawn, and these are figures that Peter also showed while we were waiting for JWST. People went out and made a lot of predictions because they were planning deep surveys with JWST, and a variety of these are mentioned here. Aaron Young did some very nice mock catalogs and simulations and made predictions for clustering. These come from Ryan Ensley et al., and they were predictions specifically designed for the JADE survey to see what you could do with both angular clustering, angular correlation. So they made mock catalogs of what they expected to observe with JADES in imaging and with spectroscopy, with near-spec spectroscopy, to measure spatial correlations. And they found the degree to which you could measure the significance of correlation functions. The spectroscopy, at least at the lower redshifts, gives you a much higher significance to your correlation function measurement. So that's the power of adding another dimension to this. Peter also showed this, which indicates how well you could study correlations between the derived dark matter halo masses, which is maybe one of the most basic things we'd really like to know about any population of objects that we're trying to study, whether it's as a function of stellar mass, whether it's a function of luminosity, whether they are AGN or not AGN, little red dots, et cetera. Getting some idea of the halo mass properties from the correlations is of great interest. And these were the predictions for what you could measure in terms of halo masses. And in this effort, they found that from the angular correlation studies, they could get down to 0.2 dex accuracy in log halo mass estimation for faint galaxies, and an improvement of about 0.1 dex if you have a fairly extensive spectroscopic survey of those same objects with near-spec. They also made predictions for satellite fractions and quenching, galaxy pairs, merger fractions, et cetera. So now people have gone out and actually tried to start measuring this. This is also from JADE's data, but actual JADE's data, not simulated JADE's data, by Del Maso et al. And very much like the figures that we saw earlier. Here is a bunch of pre-JWST measurements, and here's their measurements from the JADE survey of galaxy bias as a function of redshift in slices out to redshifts of almost 10. They are detecting significant angular clustering in these photometric redshift samples, and the characteristic increase in the bias, at least down to a fixed magnitude limit as you go out to higher redshifts. You can try to study environmental effects. So starting out with photometric redshift samples, photometrically derived samples. In this case, this study by Lee et al. Used data from several different NIRCam JWST fields, the JADES fields, SEERS, and North Ecliptic Pole surveys. They combine that all together. It's covering 185 square arc minutes. They have 3,000 galaxies with photometric redshifts at redshifts between 4.5 and 10. And then they derive local environmental measures for those galaxies in terms of nearest neighbor distance, or specifically fifth nearest neighbor distance in this case, and can separate the galaxy population out into statistically higher or lower density regions, higher than average or lower than average, and then look for correlations of galaxy properties with the environmental density. And they find weak trends, weak correlations. They find, for example, that the overdense galaxies have, on average, slightly higher specific star formation rates than galaxies in lower densities. Of course, in the local universe, higher density regions tend to have more quiescent galaxies, lower specific star formation rates. It's been known for some time that that trend seems to flatten out and even reverse as you go to higher redshifts. Elbaz et al., Cooper et al., other people found that going out to redshifts of 1 in earlier surveys, and apparently there's a signature of that even out in the epoch of reionization, that in the overdense regions, they have preferentially higher specific star formation rates. And they also found preferentially slightly redder colors, redder spectral slopes, beta, the UV spectral slope, for galaxies in overdense regions. So a little tentative, but from photometric redshifts, evidence that there are environmental correlations to be seen. This is primarily at a redshift of around 6. The photometric redshift distribution goes out higher than that, but the majority of the galaxies are between redshifts of 5 and 7. Other evidence for environmental effects, this paper by Morishita et al. In this case are now using spectroscopic data, so near-spec spectroscopy of galaxies, in this case in overdensities at around redshifts of 5.7, spectroscopically confirmed with 25 and 17 members in groups or protoclusters or whatever you want to call them at these redshifts. And they found that 27% of the galaxies that are associated with these overdensities have weak H-alpha emission with equivalent weights less than 100 angstroms versus 6% for a matched field sample. So apparently evidence for quenching, do you want to call it that? This is the opposite to what we were talking about before, where there was evidence for higher specific star formation rates in statistically overdense photometric samples, but these seem to be specifically some kind of group or protocluster type environment, and they were finding evidence for weaker H-alpha emission and a larger Balmer break amplitude for the galaxies in the overdense region compared to the field on average. Let's see, Jake was talking about this HDF 850.1 protocluster in Goods North. This is a well-studied system, first identified, well, the submillimeter galaxy HDF 850.1 was one of the very first bright submillimeter sources ever detected in one of the very first deep scuba images of the Hubble Deep Field. And for, I don't know, what was it, 14 years, we didn't know the redshift of this source until Fabian Walter et al. Measured a redshift from molecular CO lines and carbon-2 from Plateau de Boer. It turned out to be at redshift of 5.2, and it turned out to be in an overdensity. There was an overdensity of spectroscopic redshifts known from Lyman break galaxies. There was also a quasar in that structure. And now this has been studied in a variety of ways with JWST. And so this is the same data, the fresco data that Jake was showing for this, but I think there were a number of papers that analyzed this protocluster. And there are many objects now determined from slitless spectroscopy covering, from the fresco survey covering this field to have H-alpha emission corresponding to the redshift of HDF 850.1, a substantial protocluster overdensity. You can sort of see three-dimensional structure, hints of filaments. You can tell they're filaments because they drew a line through it and wrote filament next to it. And Jake also referred to another submillimeter galaxy at 5.3, which also has a big clump of galaxies around it. So interesting things there. They found no statistical differences in this study by Gerard Demanche et al. In the inferred stellar population age or the UV spectral slope of galaxies in or out of the protocluster structure. Here, Pablo Arabal-Haro, who's a postdoc at NOIRLab, or I should say he's still a postdoc at NOIRLab today. Today's his last day, and he starts tomorrow as a NASA postdoctoral program at NASA Goddard Space Flight Center. But I've had the privilege and pleasure of working with Pablo for the last 4 years on JWST science. And he has a program in which he got near-spec spectroscopy of galaxies in this protocluster. So here we can actually do some multi-line diagnostics because we're covering both the oxygen 3H beta group and the H-alpha group. So there are the protocluster members. We have a spectra of 25 of those and 50 field galaxies for comparison. And so far, in preliminary analysis, we don't see much in the way of any obvious trends when we compare the member galaxies to the matched field sample in anything we've measured so far. So here, a little similar to some of the figures that Jake was showing, We don't see, in this case, any statistical trend for, say, reddening measured from the Balmer decrement in and out of the cluster, H-alpha equivalent width for specific star formation rate, for example, or if we look at the BPT diagrams, so looking at nebular excitation or metallicity indicators, we don't see any particular trend here. Protocluster candidates. So you've just seen some examples of data in a protocluster. So before JWST, you couldn't swing a dead cat without hitting a protocluster in some field. Protoclusters, almost by definition, are everywhere. As long as you look along a long enough line of sight, you'll probably encounter something that is a protocluster structure traced by all sorts of different types of structures. But with JWST, a number of studies underway. First, again, with photometric redshifts, this Lee et al. Survey identified 26 candidate protocluster overdensities between redshifts of 5 and 7. Jake had a longer list than I have here of examples of protoclusters that have been identified with near spec. Now, in the early days, and I think this has always been true for high redshift clusters, that when you're first starting out, as soon as you find two objects at the same redshift, it's a protocluster. So that's very exciting. And in fact, one of the first ones reported by Laporte et al. In that SMACS ERO field was two galaxies at the same redshift, and so it had to be a protocluster. But we've gotten up to larger samples now. Morishita et al. In Glass had 7 galaxies at redshift 7.88 within a projected radius of 60 kiloparsecs. There have been studies of this protocluster at 6.9 around a sub-millimeter galaxy. And then there's even some suggestions that GNZ11, the famous GNZ11, may have companions at similar redshifts. Jake's talk was spectacular in terms of the work that they're doing with slitless spectroscopy. He's written a paper specifically about a 5.4 structure, but you saw much more, and you heard about the studies of quasar environments with Eiger and Aspire from Anna Christina and John's talks. So I won't go more into that, but there's a lot of interesting work going on there. And we've heard quite a bit about Lyman alpha, and Crystal gave a very nice talk about a particular structure that they've been studying in the epoch of reionization. The near-spec surveys that have been underway have been analyzed in terms of Lyman alpha emission from galaxies that have spectroscopic redshifts, and studying the 3D distribution of those. This particular study from Chen et al. Of the extended growth strip, Sears data, or these from Tang et al., looking at in several fields, including the Goods North and Goods South. In this case, combining together the Fresco slitless spectroscopy with near-spec data. The red stars in here are Lyman alpha emitters. There's significant inhomogeneity that's observed. The EGS field, for example, has a much higher proportion of galaxies in this epoch of reionization, where the neutral fraction should be high, that show escaping Lyman alpha compared to these other fields. That seems to be a statistically meaningful significance. People might like to associate this with overdensities, the idea that clusters of galaxies can ionize regions around them. I think the evidence for that is, at the moment, still not very ironclad. It's interesting. There's, some of the high equivalent width Lyman alpha emitters are in clearly overdense regions. But on the other hand, here's one of the highest equivalent width Lyman alpha emitters, and there's 1 or 2 galaxies near it, but it's nothing like this down here. So Tang et al. Conclude that there may be evidence, but it's not very clear at this point. So what comes next? What more can we do? Well, I think one of the things we can do is get a lot more spectra, because it's really the spectroscopy that is the most powerful and unique tool for JWST to be studying galaxy environment and galaxy clustering. This is a program that I'm leading. It's a large treasury program in JWST Cycle 3 called CAPERS. We're taking spectra of about 10,000 galaxies with near spec in the low resolution prism mode in 3 fields where there is near cam imaging that we can use to select photometric candidates out to the highest redshifts we can find. So it's kind of like what people have been doing in JADES and Sears, but just a lot more prism spectroscopy. We're doing 21 pointings, 63 configurations, so on and so forth. And we're really, there are many scientific applications. I'm not going to have much time to talk about it, but as I said before, as long as you're getting these strong emission lines out to H alpha oxygen 3 out to redshifts of 9, 9.5 or so, measuring redshifts for galaxies is almost like shooting fish in a barrel. It's quote unquote easy. I never thought we'd be saying that it was easy to measure redshifts at 9.5. But it is. Of course, that makes it exciting to go beyond that, and this Lyman break feature at Lyman alpha, the opacity of the intergalactic medium, makes it possible with this low-resolution PRISM data to get redshifts higher than that. But that's only a tiny percentage of the sample. We'll be targeting about 100 objects that are photometrically selected to be at redshifts greater than 9.5. But the vast majority, the 99%, are at redshifts less than 9.5, and we'll be trying to do a lot of science with these data. But the only bullet I'll focus on here is charting large-scale structure and its relation to galaxy properties. So we're hoping that with 10,000 spectroscopic redshifts from NIRSpec, we'll actually be able to see clustering and see overdense regions, underdense regions, measure clustering statistics better than we've been able to do before. This is based on Aaron Young's mock catalogs and the simulation that we did. Nothing more to say than that these ups and downs are all real in the sense that they are statistically significant and they trace the full population of dark matter halos that's underlying it. And you can just see by eye the kinds of groups and cluster type structures that we'll be seeing. Once you get out to very high redshifts, the statistics will be sparse. So it may be true, in fact, that out here we'll still be in that regime. 2 galaxies at the same redshift, it's got to be a protocluster. But down here, we should be able to actually measure some real interesting clustering statistics. Another important program for Cycle 3 is Cosmos 3D. This is the complementary approach of using NIRCam slitless GRISM spectroscopy. The PIs are Koki Kakeichi and a bunch of co-PIs, particularly folks from who are either now or were at University of Arizona. They'll be covering about 1/3 of a square degree in the Cosmos field, where there's already NIRCam imaging from the Cosmos Web Cycle 1 program. They'll be adding more filters to the imaging, but most importantly, they'll be doing the slitless spectroscopy in the F444W band, which gets H alpha at this redshift range of 5 to 7.5 or so, and then oxygen 3 at higher redshifts to do the kind of science that Jake and Christina were describing in terms of emission line, 3-dimensional diagnostics and clustering measurements. They expect to detect about 4,000 emission line galaxies. So at brighter flux limits and all emission line galaxies compared to the slit spectroscopy, but very complementary to what we'll be doing. And in fact, some of the Capers spectroscopy will be in the primer field that drills right through this. So comparing the Capers data to the Cosmos 3D data should be interesting. I really won't talk about the wide field future unless we want to talk a little bit more, but obvious things are coming from Rubin, LSST, Euclid, and Roman, both the wide field imaging over large parts of the sky, and especially combining the optical and infrared will be interesting for selecting large samples over wide areas of bright galaxies, even in the era of reionization. There's a next generation DESI experiment being planned. So after the main DESI survey is finished, a next generation survey of 1 million Lyman alpha emitters and Lyman break galaxies at redshifts 2 to 3. And then CIRMOS, which I won't have time to talk about, but it's a concept for a space-based near-infrared. It's kind of like NIRSpec, so near-infrared multi-object spectroscopy on a small space telescope, but wide field, high multiplex, covering the Euclid field, so 15,000 square degrees and 30 million redshifts with this instrument CIRMOS. The PI for that, it's just a concept at this point, but is Yun Wang at Caltech. So to summarize, below cosmic dawn, wide field imaging and massively multiplex spectroscopy, whether ground or space-based, will extensively characterize clustering and large-scale structure, at least out to cosmic noon and beyond. But JWST really enables unique narrow-field deep imaging and spectroscopic probes of clustering and large-scale structure at especially redshifts greater than 4 and out to the highest redshifts we can access. Early JWST observations are discovering and characterizing cosmic structures in the epoch of reionization. So far, there is evidence for weak trends. Jake also showed some of this. Weak trends in galaxy properties versus environment. But I would say the picture is far from clear and will be much more clear when we have a lot more spectroscopic data to work with. In particular, the interesting questions about Lyman alpha correlations that are relevant for the history of reionization seem unclear to me right now. and greatly expanding the spectroscopic data sets are the path forward. Thank you.
Thank you very much. One question from Avish.
This is a question to you, Mark, and also to previous speakers. We use the number density of galaxies that we detect of a given type to estimate the mass of the halos that are associated. Those very high masses, say 10 to the 11 solar mass of the brightest galaxies at redshift 10, indicate high sigma peaks in the Gaussian random field, maybe 4 or 5 sigma. If you use this, you can predict what the correlation strength should be. And my question is, did you try, or anybody try, to look into this to see that it's consistent with the mass that we estimate from the number density?
Well, I think that's what some of those, the simulations that Peter showed and I was showing from Ensley et al., I mean, they're turning around the other way. They're taking a simulation and seeing whether they can recover the halo masses from the clustering. So you're taking it the other way. You're saying the rare peaks are high mass objects, and therefore they must be strongly clustered. That's not necessarily true. So, for example, we talked about earlier about the stochasticity in star formation, for example, and I believe our next talk will touch on some of this. That you know, if let's say the bright galaxies, say the high redshift bright, surprisingly bright Lyman bright galaxies, are actually lower mass halos that are bursting up for a short time interval.
This will give you some noise.
Then those should be actually more weakly clustered than if they were the rare high mass objects that would correspond.
The question is this a scatter effect or is this the dominant effect?
We'd like to measure that, I think, is what we'd really like to do.
Actually, a more general related issue is this point before last, that there's no weak environment and determine effect. If the interpretation of mass and clustering is the dominant one, if you look at enough mass range, you should see a mass dependent on the environment. The fact that you don't see it, is it because the mass range selected is small, or because it's really not there?
Yeah, I don't know. I think for spectroscopic samples, that's probably part of the story is that the spectroscopic samples aren't necessarily yet sampling enough dynamic range and mass. It may also just be the statistics, that we don't have enough statistics yet to tease those things out.
Right.
Wonderful talk. You know, spectroscopy, obviously one of the most revolutionary capabilities that we have with JWST. When it comes to measuring galaxy properties as a function of environment and clustering through spectroscopy, do you have any concerns that the kind of, I'm trying to be nice, unique selection properties of JWST and the multi-field, multi-object spectrograph with near spec you know, poses difficulties, or do you feel like the combination of the slitless spectrograph with the multi-object spectrograph gets around some of the selection issues?
Well, I think that latter that you mentioned is, I won't say that it gets around it, but I think it's one of the things that I'll be interested to see if we compare, you know, to do the specific experiment, and it's not an optimized experiment at the moment, but anyway, the specific experiment of comparing what Cosmos 3D sees in the way of structure from brighter emission line objects, okay, with what we get by drilling through that with continuum selected objects with near spec. So we'll be, for CAPERS, we'll be selecting at long wavelength near cam selected. So we'll be sensitive in principle to measuring redshifts for things even with weak or absent emission lines, right? I mean, bomber breaks, things like that. If, you know, obviously it's wonderful when you have a good emission line to measure a redshift, but so we'll be taking spectra of things, not just strong emission line objects, but, you know, weaker emission line objects as well, or quiescent. And so comparing clustering statistics measured in the same fields, but selecting in different ways. We'll be probing down to fainter, so somewhat back to Avishai's point in terms of dynamic range. We'll be probing down, this is really dynamic range and line flux, but to fainter line fluxes, quiescent systems, and so on. I don't know the answer to, whether or not the limitations of target selection are going to preclude us from learning what we really want to know, but at least we can do some experiments to make those comparisons.
More questions? Mark? No? Well, then thank you very much again. So.